This is going to be on the design of hydronic snow and ice melting systems. Really, it says, what is this? To optimize performance and efficiency? Efficiency of a snow melt system? Well, maybe, but maybe not. Maybe it's actually not as expensive as you think. So this is what we're going to talk about. By the way, there is a copy of these slides on the website of my organization. So you don't have to take pictures of everything or write it all down. Really quickly, introduction. So my name is Lance MacNevin, and I'm the Director of Engineering for what's known as the Building and Construction Division of the Plastics Pipe Institute, or PPI. PPI has been around since 1950. It's a nonprofit trade association based in Texas, but focusing on all of North America. We don't make anything. We don't sell anything. We're just a trade association, but we're really, let's say, a knowledge-based, research-focused trade association. We don't do any marketing or advertising or anything like that. So what we do is we work with the companies that make plastic pipes or pipe materials or pipe equipment, and we answer technical questions that come up in the field. So we do research reports and publish things on our website for free. Everything is accessible for free. And we also try to do as much education as we can, showing how to actually use these products correctly. So that's kind of the background, the motivation of where I'm coming from. This is part of our mission, is to deliver education. And like I said, I work for the Building and Construction Division. So if you go to our website at plasticpipe.org, then just click on the button that says Building and Construction Division, and you'll get all this information for free. You can download reports or even download a PDF copy of the slides of this presentation is in there as well. The piping materials that we represent are shown here. We focus on pressure pipe materials used in plumbing and mechanical systems. So these are the common materials that you see here on the list. That's CPVC and PEX and PERT and high-density polyethylene used in geothermal systems, and two different types of polypropylene known as PPR and PPRCT. So that's kind of a family picture in the bottom of these different types of pipes shown down there. And then we focus on, like I said, the different types of plumbing and mechanical applications, hot and cold water plumbing distribution, fire protection, radiant heating, radiant cooling. As a follow-up to Haley Mick's excellent presentation in here before mine, we touch on that kind of stuff. So again, we try to do research, education, spread the good word about how these systems work and how to build them correctly. So let's get into it. What is, and I'm going to use this acronym called SIM, which stands for snow and ice melting. So it's not just snow. If you've been outside here over the last few days, there's a lot of ice on the sidewalks around here too. Even though I haven't seen much snow coming down, it's really icy out there. It would be nice if we could just melt that away and not be slipping and falling as we exit the building and enter our hotels. So this is hopefully appropriate and relevant for the time and place where we are right here. So the first question, let's introduce the topic. What is a hydronic snow and ice melt system? If you're familiar with radiant heating, how many people here are familiar with radiant heating? Per Haley's, yeah, okay. A lot of people are these days, which is good. A lot of people think of snow and ice melt systems as outdoor radiant heating systems because you build them a lot like a radiant heating system with pipes encased in concrete or under outdoor surfaces and as plastic pipes with warm liquid going through. So it's kind of like a radiant heating system, but it's a lot different from the design perspective, which is what we're going to focus on here. And of course, it isn't just straight water going through those pipes because that would freeze. So it's water with antifreeze mixed into it to prevent it from freezing when you're not running the system. But it's kind of like a radiant heating system for the outdoors. So these systems have been around for a long time. In fact, I love to collect old books. And over the years of being in this industry, I've done lots of presentations and courses and met people older than me. I'm getting to be one of those old people myself, but there's still a lot of people older than me that have wonderful old manuals that they've gathered up and collected over the years. And some people have shared a few of those with me. And two of my favorites are the one on the left from the Byers Wrought Iron Pipe Company. They have an excellent manual on snow and ice melt systems using wrought iron pipe, putting it in sidewalks and parking lots. And you can see scanning the cover and the back cover there, the two on the left-hand side. They were doing this way back in the 1940s, 1950s with wrought iron pipe. And then came copper tube. So the Revere Copper and Tube Brass Company, their snow and ice melt design manual is on the right-hand side. These are beautifully written books. They're really nice. The technology has been around for a long time of putting pipes outdoors and hot antifreeze through it and melting the snow away. We do it differently now, though, with different materials. Now we have better controls. We have good insulation that we can put under the outdoor surfaces to increase system efficiency and things like that. But the concepts have been around and been very well proven for many, many years. In fact, the full scanned copies of those books, I think you can actually get the download of both of those from the RPA website. So if you go to radiantpros.org, I think there's a little button up at the top called Archives, where you can actually download both of those books from there if you like to look. They're really well written, very classic prose, good reading. So relevance of hydronic snow and ice melt systems, here we go. First of all, safety and convenience and savings, it says. So yes, savings, not just saving people's lives, but also saving energy compared to the alternative ways of getting rid of that snow. Because we're not just going to wait till April for the snow to melt away. We have to get rid of the snow one way or another. And in a lot of cases, when we talk about energy comparisons and things like that, what we're thinking is, what else do we do if we don't melt it away? Well, in a lot of cases, you're pushing it or plowing it or using snow blowers to blow it away and things like that. Those devices take a lot of fuel and have a lot of wear and tear in outdoor surfaces and require people, qualified drivers to be driving these big pieces of equipment, which are sometimes dangerous. I remember when I was a kid, I grew up in eastern Canada where, there's snow on the ground 6 months of the year. And we have these big giant snow blowers back there, 8 feet wide, 8 feet high, because we'd get big snow. So they couldn't just push it. They had to churn it up with the snow blowers and blow it onto people's yards. And had a paper route when I was a kid, 14 years old. And in the wintertime, I remember walking to this house to deliver paper, and I see the snowblower coming behind me, but he's 100 feet behind me, and I hear this chunk sound, like chunk. And I'm thinking, what was that? And for some reason, I stood back, and where I grew up at 4:30 in the afternoon, it's dark. So I stood around, and for some reason, I decided to look up, and I looked up, and here was a big piece of asphalt curb about 2 feet long that the snowblower had actually picked up as he was trying to clear the street and widen it, and it was coming down right where I was standing. So luckily, I was able to step aside and watch it collapse there. My point is, this equipment isn't always safe. Anyway, that's one of the reasons that we like to use these systems. As I also said, for cleaning outdoor surfaces with regular equipment, all the stuff that pushes it or blows it away, it's a high maintenance cost. It costs a lot of money to hire companies to do this kind of work. Think about aging populations, baby boomers, the big wave. Maybe my dad grew up loving to shovel snow, thinking that I love to shovel it too, not so much. He's not so good at shoveling snow anymore. So a lot of our aging population, they can't do it. It's a health risk if they try to do it. So they really shouldn't. So for people like that, they could really benefit from a little bit of snow melting at home to be able to give them in and out access without having to try to do it themselves. And we are going to show that we can actually save facility owners money, whether it's an apartment building or an office building or a gas station or all kinds of facilities where you have to keep the entrances open and accessible, and you're going to pay somebody to do it. A snow melt system in a lot of cases will actually save that owner money and reduce their liability at the same time, because there's far less risk of slip and fall if you're providing nice, dry, clean outdoor surfaces. So there's lots of stuff to talk on here. Who here is familiar with the organization known as ASTM? So a lot of you guys are, okay. The American Society for Testing and Materials. They actually have a standard called, if you can read it, it's pretty small print. It says, Standard Guide for Premises Design Considering Snow and Ice Management for the Reduction in Pedestrian Slips. Sounds like a really good thing to have. Let's just follow ASTM F3627. That'll tell us how to keep our outdoor surfaces clean and dry to prevent outdoor slips. Nowhere in this document does it actually mention snow and ice melt systems, though. It talks about all the traditional ways of plowing and scraping and sanding and salting, on and on and on. That's a bit of a miss, I think, because we really have the technology to be able to do this right. Cleanly, automatically, efficiently, and cost effectively. So that's what we'll talk about here. So here's the outline of the presentation that we're going to get through. Number one, we're going to indicate the typical benefits. I've talked about some of them already, but there's even more. And then we're going to describe the 3 most common installation techniques. This isn't an installation seminar. But if you haven't seen how this goes in before, it's nice to be able to see how the pipe gets put in the ground under asphalt or paving stones to have a clue of what the systems look like. We're going to provide a list of typical applications. It's not just buildings like this or the hotel, but then we're going to spend most of the time on the 5 main design steps and actually kind of walk you through step by step. How do we estimate the amount of energy and the heat source, and how do we size the circulating pump? And then we're even going to talk a little bit about control strategies. I'm not going to get into the details of sensors and things like that. There's companies down on the floor that will do that for you. And then we are going to touch on operating costs just very briefly to give you a bit of a cost comparison. So to make best use of our time, I'll go really quickly on this part on the 6 primary benefits of a hydronic snow and ice melt system. And again, it's pretty obvious: safety, reduced risk, reduced liability, convenience, healthier, lowered maintenance costs, minimized environmental impact, and long-term reliability. This is also important. So on the topic of better safety, this part is pretty obvious. We've talked about all the ice out there already. You could rely on the guy on the left who maybe plowed the sidewalk and now is coming with the salter to do all that kind of stuff. Or on the right-hand side, big major casino entrance, they just have a fully automatic snow melt system inside there, and the sidewalk is nice and dry. So the one on the right-hand side here, much better, much safer, day and night. Don't rely on the sun to evaporate things for you. The sun doesn't always come out in the wintertime, so just do it automatically. Reduce liability. If you own a business and you have insurance, which obviously you would, then you know that slip and fall hazards are a big part of that liability insurance for your business. If you have ramps, if you have steps or a sidewalk, no matter what it is, that's a big part of liability. So do you want that sidewalk on the left to be your sidewalk where people are coming into the business? Or the one on the right hand, the middle side, the middle picture is actually Place de Ville in downtown Montreal, Canada, a major outdoor pedestrian walkway where people are entering the metro system and going to office buildings and hotels. There's a massive big snow melt system up there. It snows a lot in Montreal, and they decided, especially because of the cool granite stone they have outside, they decided it was way better for everybody, including the life of the stones, to have a snow melt system underneath than to just try to scrape it and salt it all day long. So that's pretty obvious. The healthier part, the convenient part. Well, the healthy part is try to avoid heart attacks by shoveling with snow. It's not just heart attacks, though. It's the sore backs and everything else. Now I live in Virginia, and we get big dumps of snow every few years. The picture on the right is me trying to find my car in a snowbank a few years ago. So I think I had to shovel like for 8 hours that day. That was the whole day. And that really hurt. So, you know, shoveling a lot of snow like that is not a lot of fun, even if you're in good shape and can handle it. But yeah, obviously it's healthier and far more convenient to avoid it. On the maintenance cost side of things, again, what's the alternative for any kind of commercial building that's not just your own house, or maybe you have a teenage kid you can bribe to do the driveway for you. If that works for you, tell you how much you had to bribe your kids for, and then I'll try it at home. Look at the picture on the left. This is a parking garage at Reagan National Airport back near DC. This is their snow melt system. They have a couple of pickup trucks with that, and they've got pallets of sand and pallets of salt sitting there waiting for the next snowfall. And they just spend all day scraping it and then spreading the chemicals around. Look at the entrance on the right. That's an entrance to a bank. Look at the amount of salt they put down. Probably they didn't need to do that much. That's a lot of salt. But they're really concerned with liability. Bank entrance, obviously that's where they keep the money, so they've got some. And where does all that salt go? Well, when the rain comes, it goes down the drain, which is not good for our stormwater systems and our rivers and creeks. But otherwise, people are walking into the bank and dragging that in with them, messing up the terracotta floors and everything else. Also a high maintenance cost because somebody has to be mopping that up to try to keep the salt off the floors. So we can save a lot of money by just doing this hydronically. And again, to the topic of the environmental impact, I've mentioned this a few times. If you've got some sort of a business and you're paying people to be doing pickup trucks or graders or snow blowers or whatever, think of the fuel those devices take. When you get a quote for a contract for doing snow removal at your business, and that contract is X numbers of thousands of dollars a year, however it is, that thousands of dollars, a big part of that is paying for wear and tear in the vehicles and the driver's time, but a lot of it's just paying for fuel. What's the efficiency of a diesel engine and a snowplow? Anybody want to take a guess? Yeah, 25, 30% more or less is about the efficiency you get out of a vehicle engine. The rest of the heat just goes out the exhaust or out the radiator. What's the efficiency of a hydronic boiler nowadays, a condensing boiler? Especially with really cold return temperatures? Yeah, 95, 97%. Just based on pure efficiency itself. The efficiency of our boilers is far, far better than of our vehicles for pushing it and dragging it and dumping it into dump trucks that then have to carry the snow 20 miles away and dump it into a snowbank somewhere. So it really can be better for the environment to let's just melt it and evaporate it away as compared to using mechanical equipment to scoop it and push it and drag it and everything else. So in our opinion, it is reducing the environmental impacts. And you can simply just look at that at the cost. Dale Harnt, who's at the front of the room up here, he's built a lot of snowmelt systems in Wisconsin where he's got gas meters on the snowmelt system itself. So he's got the evidence of how little energy it really takes to be doing these snowmelt systems. It's far less than what you would think. And if you look at the gas it takes to do a snowmelt system all winter versus the cost of traditional snow removal, you can actually do that comparison. And if it's less expensive to melt it, that's because we're using less fuel. Typically, the cheapest way is also the most environmentally friendly way as well. In terms of long-term reliability, this is what a lot of these systems look like when they're being constructed. It's plastic tubing going in the concrete or going under the concrete or the pavers or the asphalt or something like that. This is really reliable. As well, if you guys are in the heating business, you know that our hydronic equipment today, really reliable. Our boilers are going to last for decades. Circulating pumps, many, many years. Sensors, controls, really well proven, probably going to last for decades as well. Not going to take a lot of maintenance. Yes, sir. For drainage, yes, the question is about drainage, and absolutely. I am not going to touch much on that in this presentation because we're going to try to focus on design, but the water's got to go somewhere. The worst example I ever heard of was somebody built a snowmelt system in their residential driveway and didn't put a drain in the end, so all their water drained out onto the street and made a big iceberg in the middle of their street, and they got in trouble. So they had to shut it off. So yes, you need to have drainage, either drain it to natural sod or into a pool or something like that, or put an actual drain in there at the low spot to capture that water and put it down a storm drain so it doesn't create a hazard somewhere else. So good question, thank you. So in terms of the reliability, if you're new to plastic piping, which is my background, my world for the last 30 years, the types of piping materials that people are using for snowmelt systems, it's pretty much these two tubing materials right here. There's PEX, or cross-linked polyethylene, which was first sold and first produced in 1972 for radiant heating systems in Sweden and Germany. PEX has been around for more than 50 years now. This is not new. And then the other material known as PERT, or polyethylene of raised temperature, was first introduced in Europe in the late 1980s, which, you know, that's a long time ago too. My kids tell me. The 80s doesn't feel that long ago to me, but yeah, if you weren't born yet, that's a long time ago. These tubing materials are really strong. They have a burst pressure of well over 500 psi in terms of just blowing them up, even a small diameter half-inch tubing. Very, very strong. The long-term pressure ratings as shown at the top, even at 180 degrees Fahrenheit, which is not the temperature we use in snow melting because concrete can't withstand 180 degree water going through it. But these products are pressure rated for 100 psi continuous use, even at elevated temperatures like that. So these are products that are not going to break down, not going to rust, not going to corrode. They can withstand the heat. They're very well suited for these applications. They're not going to create a problem out there in the outdoor surfaces. And they're made to really rigorous standards, so a list of the product standards are shown there. And then even for the piping we use in the indoor mechanical rooms, larger diameter piping in a lot of cases, you might have 2 or 3 or 6 inch diameter piping in the mechanical room, depending on the overall size of the system. Those products don't come in like 3, 4, 6 inch diameter. At that point, we're probably going to use the materials known as CPVC or polypropylene, which are also both really well suited for indoor hydronic piping. So you can actually build these systems with all plastic. That way you don't have to worry about any rust or corrosion or anything like that. You would still be insulating the pipes indoors to keep the heat in and things like that. But also if you have long runs, let's say you have a distribution manifold out at the end of a driveway that's 100 feet away from the mechanical room, how are you going to get the fluid from here in the mechanical room to 100 feet away, way out there? Well, what a lot of people do is buy pre-insulated flexible plastic pipe, like the image on the right-hand side. So there's 2 PEX carrier pipes in that, a supply and return, inside a waterproof outer casing surrounded by polyurethane foam, which is semi-flexible, so it comes in a coil. And if you need a 120-foot long loop, you can just buy that and have a 120-foot piece of pipe continuously from the inside to the outside. No joints, no connections, just put a fitting on each end. So it's really easy to actually build these piping systems, and they're going to last for decades and decades. So reliability is provided. So that's the summary. Hopefully some of that was obvious, and if not, eye-opening. We hope it was interesting. Now, in terms of how you build these systems, before we get into design, let's just talk about how we actually get the pipe out there and what these systems look like. And we have 3 cool drawings on the bottom here showing the 3 major installation types. The first of these is poured concrete. The second is interlocking pavers or paving stones. And then the third of these is asphalt, which is the scariest one of all. But almost every type of outdoor surface can work with a snow melt system. For the ones with concrete, it's really just like a radiant heating system. First, you want to have insulation down on the bottom to keep heat from going down and make sure it all goes up. And then you put your tubing in. Now, where that tubing should go, because with a lot of radiant heating systems, people are stapling the tubing down to the insulation at the bottom and then pouring 4 inches or 5 inches or 6 inches of concrete around the radiant heating system. Response time in an indoor radiant heating system, often not so important because it's constant heat loss. With an outdoor snow and ice melt system, we're often starting these up from a cold start. Response time really important. So in a lot of cases, it's recommended to keep the tubing just 2 to 3 inches down from the top surface, not at the bottom of the slab. So if there's going to be a wire mesh or a rebar, in a lot of cases there's rebar to reinforce the concrete, you want to place the tubing on top of the rebar so it's in the top half or sometimes even the top third of the concrete slab. And that's primarily for response time. So when you turn it on, it warms up more quickly. But keep in mind also, concrete is not a great conductor of heat. And the more concrete you have to drive that heat through, the higher the fluid temperature is going to have to be. So if your tubing was 6 inches down the bottom of the concrete slab, you're going to need a higher water temperature to drive that heat up through and make the top of the concrete warm than if the tubing was in the top third of the concrete. So it's better for overall system efficiency if you can keep the tubing in the top half as opposed to the bottom half. Here's some great pictures here. This one, they didn't do that. The tubing is actually down near the bottom. This was a relatively thin concrete slab in this building because it was just a sidewalk entrance into a building. This one here, it's a big driveway. It looks like the tubing is lifted up a little bit. You can see how they're pouring the concrete around the tubing. And in most of these layouts, you're going to see the spacing of the tubing being as consistent as possible. If you ended up having most of the tubing at 8-inch on-center spacing, but all of a sudden for some area it was at 12-inch or 15-inch on-center spacing, that gap between the 15-inch spaced tubes would not melt for a long time. You'd end up with snowy spots or icy spots for many, many hours after the rest of it had melted nicely. So consistent tube spacing, lots of tubing density is really important. Now when it comes to pavers or paving stones, pretty simple. Again, you want to put an insulation base down first. In this case, we can actually staple or clip the tubing to the insulation base at the bottom, and then we're going to put a pretty thin layer of sand compacted around the tubing. That sand is now our thermal mass conducting the heat away from the tubing, so you want it to be as dense and compacted as tightly as possible. And then, but they're going to put sand anyway under paving stones. So the guys who do the paving stones are probably the same guys putting the sand bed down and then putting their paving stones on top of that. So this is pretty straightforward. By the way, there's an association out there, ICPI.org. I think that, if I remember correctly, that's the International Center for Pavers. I forget what the I stands for. But at the ICPI.org, they've got some pretty good cutaway drawings of actually how to build a snowmelt system with paving stones. So my advice came from them, the guys who actually put the paving stones in. Here's a good picture of that one going down. Again, you see tight spacing of the tubing. And here's one that's working. It works nice and clean. If you see a proper snowmelt system, you'll always see this nice, crisp, clear edge at the edges of the heated area. Now, asphalt. If you want asphalt, because a lot of people just want asphalt because they like the look of blacktop. So that's why they want to have it. And in cold climates, it's more flexible sometimes than concrete. So it's nice to have because it has some give if the earth is moving and shifting and things like that. But we cannot actually embed plastic tubing inside hot asphalt that's 350 degrees. The plastic tubing that we're using here, it'll withstand 200-degree fluid temperatures with pressure inside. It'll withstand 250-degree temperatures with fluid inside. but it will not withstand 350-degree temperatures with fluid inside. If you tried to actually embed it directly in hot asphalt, that tubing would soften and would squish flat, and then when the asphalt cools, your tubing would be, the shape of a pancake perhaps. So you're not going to get very good flow rate through that. So the important thing for doing this with asphalt, as we see in the drawing here, is we're putting down an insulation base first, putting the tubing down, and embedding the tubing inside sand or stone dust. So we've heard it recommended that stone dust is really a good way because it compacts very tightly. Again, air voids are bad for heat transfer. So the most compact media we can get around the tubing, the best for better contact and conduction of the heat. So stone dust is often used there. And then the guys with the asphalt can come and start placing the asphalt. However, you don't leave. If you're the contractor, you don't leave and walk away. You have to make sure all your tubing is connected up to your distribution manifold and that your distribution manifold is connected up to a source of cold water that you can regulate. So the really important part of this is once they start placing that hot asphalt down, again, which could be 350, even 400 degrees Fahrenheit, you need to be flushing water through the tubing to carry the heat away from the tubing. That's what protects the tubing and keeps the tubing from getting soft and flattening out under the weight of the hot asphalt. This could take hours. If it's a hot sunny day in the summertime with sun beating down on the asphalt, as you know, it could take 12 hours for the asphalt to cool off. So the way the contractors have done this is you measure the temperature of the water coming out of the tubing. You control your valves to make sure there's enough water coming out that the temperature of the water coming out of the tubing is 150 degrees Fahrenheit or less. If the water is getting hotter than that, increase the flow rate. Pass more water through the tubing. If the water is way colder than that, then you can start to close off the valve. You don't need as much water going through, so you can reduce the water usage. And then eventually, when you realize the asphalt's cold now, then you turn it off. But it may take hours of sticking around to flush the water through before you get that problem solved. But here's a project here. This was years and years ago when I took this picture, but that's a nice asphalt system built exactly like that. So it definitely works. The other way of doing asphalt systems, and some people will do this too, is instead of the stone dust around the tubing, is they pour concrete around the tubing, which seems a little bit more expensive, and it is, but it's also more secure as well. And the concrete is going to conduct the heat better than the stone dust, I think. So I talked to a guy in Philadelphia area last week that is doing a system, 5,000 square feet residential driveway. Yeah, I know. I want to see that house. That's a big driveway. Anyway, what the homeowners want, they want asphalt for the look, but they've decided they're going to embed the tubing in concrete first and then pour the asphalt on top of that. Now, it turns out the guy who contacted me used to be a concrete contractor, so he might have had some influence in terms of telling them do concrete first before the asphalt, but that's the way they're going to go. There's a few slides here on the importance of insulation, because where do we want our heat to go in a snow melt system? Up, obviously not down. And if this is a cold start, if it hasn't snowed in 3 weeks, we're not going to keep that snow melt system in the driveway warm for 3 weeks waiting for the snowfall to come. You could, but I wouldn't recommend it for an energy and environmental standpoint. So again, usually these systems are cold start. If this is our concrete slab and this is our frozen earth is probably more than 2 inches thick. In fact, it's probably about, 12,000 miles to the center of the earth. There's a lot of frozen earth down there that's really cold. And when we fire up this snow melt system, we don't want a lot of our energy to go down. We want it to go up. So if you don't have insulation, you could easily have 50% of your heat being sucked into the cold earth, especially at startup when you're trying to warm the system up for the first time. So it's really important to have insulation. In a lot of cases, you don't need a ton of insulation, but imagine this is 1 to 2 inches or maybe 1.5 inches of like a styrofoam SM type insulation down below here, something rigid. It could be something flexible, but as long as it can withstand whatever traffic's going to be on top of it and it's durable and things like that and it gives you a good R value. Now my red arrows pointing down are a lot less than what they were a minute ago because there's still going to be a little bit of downward heat transfer with insulation. It doesn't block downward heat transfer completely, but it greatly reduces it. So that's overall better system efficiency. So here's just a couple of pictures. The one on the left is an old church with stone steps, very uneven and worn after 100 years of shoveling and everything else. So they actually sprayed polyurethane foam on that. to be able to encase those old steps in insulation, and then did an overpour. And then the one on the right, we'll hear about that project on the right-hand side later, but there's nice extruded polystyrene foam board insulation below that. Most of the codes, whether you're in Canada or the US, our mechanical codes talk about snow and ice melt systems, and they generally say you have to have a minimum of R5 thermal resistance below a snow and ice melt system. So that would be like 1 inch of foam board insulation. But in this case, a little more is a little better, and will give you better overall efficiency and response time. So generally 1.5 to 2 inches is what's used. Plus it's also stronger. For the foot traffic walking on it, 1 inch foam board, not super strong. If you have 1.5 inches, it withstands a lot more foot traffic without cracking and breaking. And there's a cool picture there of an insulation product that has all these knobs on top of it. So the contractor was able to just step the tubing into the knobs, and the knobs hold the tubing in place without any staples. And you see it's kind of a nice, beautiful curved driveway and everything like that. Looks really nice. With flexible plastic tubing, it's easy to build these kinds of systems. So that's kind of our glimpse into different ways of installing these systems. That's not all there is that you need to know, but at least that gives you an overview. Now the next part is a list of different applications. So one more thing before we get into the design steps. This is a list of, let's say, the 10 most popular types of applications where you find a snow and ice melt system. The image here is actually a ski lodge, as you can kind of tell by the ski lift over here. Ski lodges, obviously people are going there all day long in the wintertime. Also very popular locations for radiant heating inside and snow and ice melting outside. But when we talk about sidewalks, sometimes when I talk about a sidewalk, I just mean a private home. That's a pretty nice looking private home. They've got a lot of snow melt there. That's one way of doing it. How about public sidewalks? This is a picture of Holland, Michigan. If anybody's ever heard of that, the IAPMO e-official magazine just ran a really nice story about the downtown snow melt system in Holland, Michigan. It's been there for more than 30 years. It's a very snowy place, and the downtown merchants wanted to have good access in the wintertime for people to be able to come downtown and get around and enter their businesses. So they built a snow melt system about 30-some years ago, and most of it is actually powered by waste heat, as I understand, from some sort of industrial facility downtown. So that's a great example there. Here's another building entrance under construction. Here's a municipal building on the right-hand side. In the snowstorm, you see it's working well. When you're looking at sidewalks, again, and we'll talk about this more in the design part, you can do maybe 150 to 250 square feet of outside area per one loop of tubing. Because as the fluid travels through the tubing, it gives off its heat and gets cold. So you can't have like a 1,000-foot circuit of tubing for radiant heating, or especially for snow melting. So even a room this size, if this was an outdoor sidewalk, what is this room, about 1,000 square feet or something, we'd probably have maybe 5 or 6 circuits of tubing in a room this big connected to a distribution manifold that could be copper or plastic or brass or stainless steel. Where are we going to put those manifolds? Sometimes we put them outside in a vault in the ground, or in the picture here in the lower right, if you can see that one, it says snow melt. You can't really read it, but that's downtown Anchorage, Alaska. They've actually have snow melt and all their downtown sidewalks, and they actually have these vaults to hold the manifolds in it. So that's a pretty cool thing, and that's where they put them. And then here's another hotel entrance to keep people safe. Steps and stairs, big fall hazard, right? There's different ways of doing snow melt and steps and stairs, but an important thing is you want the tubing not embedded deep in the concrete, but kind of close to the actual surface where the foot traffic is going to be. So here's concrete that was done as a ref pour, and then the tubing was actually stapled into it or held in with little concrete anchors to hold down before more concrete was poured. Here's a different one, maybe not the best installation because the tubing is kind of deep inside, and this part here isn't going to transfer the heat so well on that one. The one on the right, see they built little formwork around each of the steps for pouring concrete inside. So they put the structural part down first, put some tubing down, now they're going to pour more concrete, and then the tubing will be in the top. This is a precast concrete step for residential application. They just anchored the tubing on top of it using some plastic clips, and now they're going to, in this case, they actually put stone on top of the concrete, so they put a mortar bed around the tubing and then set the stone into the mortar bed. And also it's going to be safe. So here's some drawings that make that part I was talking about a minute ago a little more obvious. If the tubing And drawing number 1 is way down at the bottom. Really easy to install that way, but look at how much concrete the heat has to go through to actually melt the surface. That can take a long time if that's 8 or 10 inches of concrete. So it's much better to kind of build it up this somehow like this, so that the tubing is much closer to the top surface. Faster response time and just better system effectiveness. So that's a good drawing there. And then there's another drawing kind of showing how to route the tubing. In steps like this, where you want a relatively thin diameter and flexible tubing, people are typically using nominal tubing size 1/2. So 1/2 inch PEX tubing or PERT tubing to do these kinds of step systems, where you don't need really long circuit lengths anyway. Other applications, how about outdoor hot tubs? Who wants an outdoor hot tub in the wintertime to be able to walk out and go sit in the tub when it's like 20 degrees outside? I want that. However, I don't want my feet to freeze to the pool deck as I'm getting to my hot tub, or especially getting out of it. So a lot of people will put these snowmelt systems around outside pools intended for wintertime use. Think about what you could also do that in the summertime. If it's really hot and the pool deck actually gets hot in the summertime, you could actually continue to circulate the water through there and use the pool deck as a bit of a solar radiator and collect that heat through a heat exchanger and use that to help heat the swimming pool and transfer the heat into the water, into the pool. So that's overall efficiency. Driveways. Here's a house we looked at before, really nice driveway. That's a big driveway. They've got snow melting there. Here's another driveway with pavers, another driveway with patterned concrete and different colors in it. Look at this driveway here, stained, patterned, colored concrete. Do you really want a plow driving across that, scraping all that up? I would not if that was my driveway. And then here's another beautiful driveway here. This is a big commercial one, and you can see it's in operation. Here's where the street stops right there, and then there's drains down here somewhere at the low spots. Ramps, pedestrian ramps look like that. Here's some more pedestrian ramps, one like that. Vehicle ramps for underground parking garages. Here's at one of the Smithsonian buildings, downtown Washington. This image on the right is an apartment building with a ramp into the apartment building. We're going to see that picture again later. How about roadways? Let's be audacious. Let's just snow melt the whole street. They do that, especially in the mountain areas, Colorado, Utah, places like that, where people go there to go skiing. They want people to be able to get there and get in and out all through the winter. And, you know, the ski hills are typically built in areas where it snows a lot. So here's an entire roadway being done. And believe it or not, I just saw this online a few weeks ago. The town of Vail, Colorado already has a snowmelt system, but now they're thinking of putting in geothermal heat source to actually power their snowmelt system. That's a pretty neat idea. It's going to be really expensive to do it, but it's Vail, Colorado, so they may do it anyway for the greenness of it. Parking garage ramps. Here's more of these for a parking deck here and then underground parking over there. Here's a parking garage. This is the roof of a Toyota dealership in downtown Manhattan, New York City, where they actually, you know, they're parking their cars out there. You're in New York City. Where are you going to park all these cars that you're selling? Well, you park them up on the roof. What if somebody wants to buy a car today and it's snowing? You just snow melt the top of your building so the snow doesn't build up there and so the cars are still accessible. This is not a clear picture, but this is downtown Manhattan, and that's a snow melt system up there in the roof deck. Train stations, lots of people coming and going. We need good, clean access. So there's a big train station downtown Toronto here and commuter train platform over here. Trains are going really close to the people. You do not want slip and fall incidents happening there, so public safety. Aircraft hangars. What about aviation facilities and things like that? Even big aircraft hangars often use radiant heating inside as a really efficient way to heat the building and warm up the planes more quickly and stuff like that. But if it's wintertime and there's snow blowing up against the doors, those could freeze. So you could also do basically some tubing embedded in the doorway so that the doors can actually remain operational during really bad weather as well. And then if you think of other things going on at aviation facilities, taxiways, loading docks where people are coming and going and stuff like that, all of those things are good candidates for snowmelt. Anybody here ever been at DFW Airport before? Yeah, you go there a lot. They've got an overhead train system, right? It's called the Skylink. And that train, like a lot of trains these days, runs on rubber tires on a concrete track. Dallas doesn't get a lot of snow, but they get a lot of ice. Several times a year they get these big ice storms. What if this concrete track was covered in ice? How well is this rubber-tired train going to be able to get around on a slick of ice? Not so well. So that's all done with a snow melt system as well. And that was put in about 15 years ago. So you don't see it, and they don't turn it on very often, but they actually have their own weatherman at the airport. And if he hears there's an ice storm coming, he calls operations and says, activate the snow melt system for SkyTrain so they can keep that train going. And then this one here is a medevac helicopter landing pad on the roof of a hospital. Holy cow. If you're coming in a medevac helicopter into the roof of a hospital, there's a bit of an emergency going on. You don't want people slipping and falling up there. You would like that to be easily accessible to get into the building. So those are some good examples. And then the 10th example here, pretty special, turf conditioning. Anybody watched a football game with the Kansas City Chiefs last week where it was really, really cold? They actually talked about how they actually have a turf conditioning system under the field surface there. They have natural grass. If you're an NFL player and it's 10 degrees outside, how soft is that grass going to be when you get tackled? Not so much, right? It's frozen hard earth. So in most of the NFL fields nowadays, they have turf conditioning systems inside, underneath the grass. So it keeps the grass green and growing, even in the wintertime, but it also keeps the soil nice and soft so that when the players get tackled, these guys being paid whatever, $5-8 million a year, you don't want them getting all ripped up by falling on top of frozen earth. So this is a practice field here. There's no stadium, but this is another one, an actual stadium. And most of the football stadiums built in the last 15 years have these systems inside if they're using natural sod. So that's a lot of examples. Each of these systems, though, has its own design considerations. So finally, we're going to get into the design steps. So there will be some math involved. If anybody has to leave, there will be numbers involved with this part. When you think about it, doing the calculations for a snow and ice melt system, it's kind of straightforward. The first thing we have to do, let's say it snowed, it's 20 degrees outside, and there's lots of snow fell down. Well, we know the melting point of ice or snow is about 32 degrees Fahrenheit, right? Or 0 degrees C. So the first thing we have to do is warm that snow or ice up to get it up to the melting point. So that's kind of step one. And we know how much energy it takes per pound of snow or ice to actually warm it up per degree. The next thing we have to do is what they call the phase change. We have to melt it. And it takes a lot of energy to put into it to convert it from frozen water to liquid water. But we know how much that is. It's 144 BTUs per pound of ice at 32 degrees to make water at 32 degrees. So we can calculate that. And then in a lot of cases, we want to evaporate the water if we don't have good drainage or if we're in a hurry to get rid of it. If you have good drainage and allow that water to drain off, that's going to take a lot less energy compared to a perfectly flat system where you have no choice but to evaporate it. So when we do these systems, we're going to keep those parts of the design element in mind. Now, this is a really loaded question here, right? Can we realistically design a snow melt system that'll function for every possible weather condition and every possible situation? A blizzard up here, could we snow melt that sidewalk or that street and guarantee the residents, don't worry, no matter how bad the whiteout, at minus 20 Fahrenheit and blizzard conditions, we'll keep your streets snow-free? With a nuclear device or an unlimited amount of energy? We probably could, but it's going to cost a lot. How many people here are engineers? Hand up for an engineer. Okay. So if somebody asks you, can you do it? What's your answer? Usually we can do it, but it's going to cost you, right? So when it comes to designing snow and ice melt systems, we don't typically design them for the worst possible weather conditions because people probably aren't going to be driving when it's a whiteout and stuff like that anyway. But when it comes to designing and figuring out how many BTUs we need, here's the things you need to keep in mind. And this is a lot more complicated than just doing the heat loss calculation for a building. Because for doing the heat loss calculation of your building, do you care about whether it's windy or not, sunny or not, stuff like that? No, you just kind of design around worst case conditions. So we have to pay attention to the slab temperature at the start of snowfall. So if it's 18 degrees Fahrenheit outside when the system kicks on, we're going to have to warm that up to get it ready to start melting. The air temperature is important. The rate of snowfall, is it half an inch an hour or 2 inches per hour? That matters. How about the density of the snow? Is it light, dry, wispy snow, or is it heavy, wet snow? It's going to take more energy for heavy, wet snow. The wind velocity also is important. And then what about these last two? Apparent sky temperature and the humidity level. Well, those are important because we have to evaporate the water away in a lot of cases. If it's really humid outside, it's going to be harder to evaporate moisture off our slab than if the air is dry. And the apparent sky temperature also has to do with evaporation. So I didn't make these things up. This information is actually found inside an ASHRAE handbook chapter, which we'll look at in a second. So we need to gather some information. And then here's the steps we're going to go through for designing the hydronic system. First, we're going to select the appropriate level of performance for the customer. I'll show you how to do that. Then we'll design the system for the required heat output. That means how many BTUs per square foot do we need our hydronic system to deliver. Then we can select and size the heat source for this. Little one, big one, depends. Then we'll design the piping system to be able to deliver that much heat to the outdoor area. And then we'll size the rest of our hydronic equipment, like the circulating pumps and expansion tanks and all that other stuff in the mechanical room, once we know how much liquid, what temperature it needs to be, and what the flow rate is. Then we can do the rest of the mechanical room. So the first part of this is select the appropriate performance level. And this sounds a little crazy because if I said design a heating system for a house right here in Chicago, you wouldn't ask me, how comfortable do you want to be? Do you want your heating system to work when it's 10 degrees outside? Or if it only works when it's 20 degrees outside, is that okay with you? You wouldn't do that, right? You wouldn't really get the customer involved to say how good they want their heating system to be. You just follow regular things and design it for the outdoor air temperature, kind of the expected coldest day of the year. But for a snowmelt system, if we try to design for the worst possible weather conditions, it's just going to be really expensive to, specify massive boilers and pumps and pipes and everything else. So a lot of this information, though, is going to be found in this ASHRAE book right here called HVAC Applications, which most of you probably have that. Used to be Chapter 51. They've just changed it to Chapter 52. So I fixed that in my other slides. So Chapter 52 is on snow and ice melt freeze protection. And it includes tables showing frequency of snowmelt surface area heat fluxes. And those tables include the terms snow-free area ratio and frequency distribution. Basically, the customer gets to select how capable the system will be. So there's about 45 cities in this table inside Chapter 52. Now fixed it here at Chapter 52. There's about 45 tables in there. If you're designing a system for a city that's not in that table, select a similar city or a city with similar weather. Otherwise, you're going to have to do 14 extra calculations on your own to calculate the BTU requirement. So here's an example of the table. And this is, I don't know why I picked Madison, Wisconsin. Do I know anybody in Madison? In Madison, Wisconsin, here's how the table works. First of all, it tells us on average there's 161 hours per snowfall a year. That's how many hours the system would have to operate. And then it gives us 3 rows for snow-free area ratios. And then these columns for frequency distribution. Basically, what 1 means is we want the outside area to be 100% snow-free. 0 means 0% snow-free during snowfall, which means it's okay to have some snow in the outdoor area. And it takes a lot less energy to do 0% free versus 100% free. 4 times more energy to keep the outdoor surface 100% snow-free during the snowfall. And then 75% means we could keep it 100% snow-free during 75% of historic snowfalls in Madison, or 90% of snowfalls, or 95% of snowfalls. Look at this. If we were designing a system in Madison to be able to keep the outdoor area 100% snow-free during 100% of all known snowfalls in Madison, Wisconsin, we'd have to design that system to supply 449 BTUs per hour. That's kind of ridiculous. That means the boiler, the pumps, the pipes, everything would have to be designed around that capacity, when rarely would anybody ever expect that or want that anyway. So this is where the customer gets involved and selects how good they want the system to be. So when we talk about a system being 100% snow-free, an error ratio of 1, that means there's no snow on the outdoor surface. We're melting the snow as fast as it falls. If we talk about the AR being 0 or 0% snow-free, that means we're still melting snow, but we allow there to be a little cover of snow on the top surface. In a lot of cases, that's okay. I can still get around if there's a ½ inch of snow in my driveway. And it takes a lot less energy to do this at the bottom because you know what? Snow is a good insulator. So if we allow there to be a little bit of snow on the outer surface and just melt it from the bottom, then we're actually protecting the snow melt surface from the wind. And then in the middle, we have an AR of 0.5, meaning it's about 50% snowfall, free of snowfall during the storm. And that could look like that for an AR of 0.5. In terms of what should we recommend to our different customers, here's kind of our recommended table for different types of outdoor surfaces. I'm going to focus on the one that says commercial parking ramp. You probably want that 50 to 100% free of snowfall because if it's a ramp, you need to drive up it. But frequency distribution, if you can keep up with 90 to 95% of historic snowfalls, that's probably enough because if it's snowing worse than that, people probably aren't going anywhere unless they're an ambulance or a fire truck or police or something like that. So this table is just kind of our advice. And like I said, there's a copy of this presentation on our website. So this table is part of that presentation online. And then this other column is just the actual BTUs for different places. Really quickly, we're going to do a design example for a building that actually exists. This is an apartment building that has a ramp that's conveniently 1,000 square feet. It's 20 feet wide and 50 feet long, which works out to 1,000 square feet. And this ramp is in Albany, New York. Why did we pick Albany? Because Albany is the very first table on the list of cities in the ASHRAE handbook, because it starts with A. But it's also a pretty snowy, wintry place. If you look at New York State, here's Albany way up here. So it's not right in the lake, but it's a pretty cold place. So it's a bit of a challenge. The ramp is going to be built with 6 inches of poured concrete, which is important to know because every time we turn this on, we're going to have to warm up that concrete. And the owner of the building says, I want this ramp to be 100% snow-free up to 90% of historic snowfalls. So 90%, that's when my people need to be able to come and go. If it's snowing worse than that, they're not going anywhere. They can come in, they're just floating downhill, but they probably don't need to go out and exit the building at that point. If it's worse than a 90% snowfall, that means we're still going to melt snow, but not keeping it 100% snow-free. So this is what the customer has asked for based on a conversation of, it could be twice as expensive to make a system that'll keep up with 98% of snowfall compared to 90%. So this was what the customer asked for. So to come up with my BTU requirement, I go to the ASHRAE table. Again, this should say Chapter 52 because they changed the chapter number. It's called Table 1. And I find Albany, New York at the top of the table. And I go to AR value of 1.0, meaning 100% snow-free, and frequency distribution of 90%, which is what the customer asked for. And that means the system has to output 125 BTUs per square foot. At 95%, it would be 149. At 98%, it would be 187 BTUs. So it kind of goes up on a sliding scale. That means we need to design the system to meet the customer expectation for 125 BTUs per square foot output. So this is one way of coming up with the number. Now, a lot of you will know, if I know that number, I got the rest of it from here, right? I know how to design a system to output 125 BTUs per square foot. But don't forget about a couple of other things. One of them is the downward loss. Even with insulation, there's still downward loss because you have X number of billions of tons of frozen earth down below you. So even with insulation, ASHRAE recommends to count on 20% downward loss. So we take that number that we need, the heat going up, multiply it times 1.2. In this case, then, our required output is 150 BTUs per square foot going up. Now, each time the system warms up, we're going to be doing a cold start, and we have to warm up the concrete. This isn't really important for the design, but it's important for energy calculations over an annual period. So when I show you the annual operating cost a few minutes from now, just keep in mind that I'm assuming that every time the system starts, it's pretty cold, 18 degrees Fahrenheit on average. And what we normally want to do for a snow melt system is get it up to 38 degrees concrete temperature to be able to melt the snow away and overcome wind loss and things like that. So that would be a 20-degree temperature pickup that we have to go from cold start to melting situation. And based on concrete, we know the specific heat of that in terms of how many BTUs it's going to take to warm up a concrete slab. That's just math and numbers. We can calculate that. And in fact, for this ramp that is 6 inches thick of concrete and 1,000 square feet, every time we warm that ramp up from 18 degrees Fahrenheit to 38, it's going to take about 345,000 BTUs of energy to get it ready to melt each time we pick it up. If it snows 10 times a year, it's that times 10. If it snows 20 times a year, it's that times 20 to come up with your annual energy consumption just for the pickup temperature, separate from the actual melting temperature. But it's just math. We can do this in an overall calculation. Now, what should we use for the actual heat source? And I know I'm running out of time here, but I started 5 minutes late, so I might have to push it to 5 minutes late. In terms of our heat source, you've got a lot of applications, or a lot of choices, I should say. You could have a dedicated boiler. You could use a shared boiler that's also heating the house and the hot tub, but make sure that there's antifreeze in the outdoor part. You could use geothermal. You could use biomass or an outdoor wood boiler. They've got these cool new gas absorption heat pumps here at the show. Could be waste heat. If this is a commercial building, a data center, cooling, something like that. You could actually use the parking lot to help the data center reject its heat all winter long, even if it's not snowing. So there's all kinds of applications there, or choices for the heat. So that's all kind of leading us up to how many BTUs we need to output from the system. It's 150 BTUs per square foot times 1,000 square feet. 150,000 BTUs per hour is what we need our heat source to do. In terms of what this tubing is going to look like in the outdoor area, here's some general advice. And every system is different and can be customized on its own, right? But most of these commercial systems, we're going to be using 3/4 diameter tubing. If you're doing a residential driveway, people often use 5/8 diameter tubing there. 5/8 is a bit smaller, way more flexible, easier to bend tightly. And then for steps and stairs, we're often using 1/2 inch diameter tubing, as it shows at the top. In terms of the spacing, you've seen this on lots of pictures and drawings already. We're not doing 12-inch spacing of the tubing with the snow melt system. You'll get strips of snow in between. So 6, 8, 9-inch spacing is normal, so it works out evenly. And then depending on the tubing diameter, that has a big impact on your circuit length, as well as the actual load has a big impact on your circuit length as well. So in this system, and this is a real system, it exists. This was the design for it. It was built with 3/4 diameter tubing at 8-inch on-center spacing, which works out evenly for something that's 20 feet wide. All these tubes can be exactly 8 inches across. And then the designer chose to keep the circuit lengths to 250 feet and keep every circuit really close to each other in terms of the total circuit length, so that they're kind of self-balanced. You don't need a balancing manifold if all your circuits are the same length. And there is a drain down at the bottom down here to catch the melted stuff. Now, how much tubing is that? If we're doing 1,000 square feet at 8-inch on-center spacing, you can actually just do 12 inches divided by 8 inches, works out to being 1.5 feet of tubing per square foot of concrete. That's just kind of an illustration of 4 square feet with how much tubing would be involved with something like that. So to find the total amount of tubing, it's 1,000 square feet of area times 1.5, which means 1,500 feet of tubing. And if we're going to do circuit lengths of about 250 feet, that means it would be 6 circuits all about the same length. And that would work out well. Remember, our total heat load was 150,000 BTUs per hour. If we're delivering that through 6 equal length circuits, then it's going to work out to 25,000 BTUs per hour per circuit. It's a lot more than what we do with radiant systems. But that would be just, again, following the math, 150,000 divided by 6. And this is peak loads. Every time it operates, it doesn't need that much heat, but we designed for worst case situation. Here's our design, and there's the actual ramp that was built according to that design. So that's what it looks like. So hopefully you can visualize that. In terms of then, what does this manifold look like and that kind of stuff? Here's a manifold with 6 outlets. It could be brass, it could be stainless, it could be plastic. Different companies have different manifolds, but we want 6 circuits, all the same length. And in terms of calculating the flow rate, most of you probably know the flow rate calculation, which takes into account the delta T, the maximum temperature difference between supply and return, which we normally use 25 degrees Fahrenheit as delta T in a snowmelt system. And then since we're going to be using 50% polypropylene glycol for freeze and slush protection, that goes into the equation as well. So for 150,000 BTUs of heat being delivered, divided by this value based on the delta T and the capacity of the fluid with glycol, we're going to need 13.6 gallons per minute flow rate. If we divide that by 6, that's 2.2 gallons per minute per circuit. That's how much flow rate of tubing needs to go through each of these circuits. Now, how do we calculate the head loss through the tubing? Because this is important when sizing a circulating pump. You need to calculate the head loss or the pressure drop through that. Well, there's a free online tool you can use called a plastic pipe design calculator at plasticpipecalculator.com. And this has been around since 2015. This is not new. This was actually designed, it's our organization's website, but it was built for us by the Avenir company up in Calgary. But if you enter in, you select PEX, 3/4 tubing, 2.2 gallons a minute of flow rate per circuit. Each circuit is 250 feet long, and I've got 50% propylene glycol. Put in your fluid temperature. I said 60 degrees Fahrenheit because it's going to be colder at startup, but hotter in operation, so that's kind of average. And that shows you the head loss over here is going to work at about 13.9 feet of pressure drop or head loss per each circuit. But all circuits are the same. And then the velocity, by the way, in case you're curious, that fluid is going to be going at about 2 feet per second at that flow rate through those tubing circuits. So when it comes to sizing the circulator and everything else in the mechanical room, I'm not getting into those details. But let's say we've got that was our flow rate. Let's say our total head loss is 25 feet of head loss. That's the head loss through the distribution tubing that we just did, plus the head loss through the boiler and other mechanical room components, the manifold and stuff like that. So basically you just select a circulator that'll do that many GPM at that much total head loss. And that allows you to size the circulator. And all the pump companies have online calculators. You just type in, I need this much flow at this much head loss, and they'll tell you what circulator to use to supply that flow rate. So that's kind of the design steps. And I know I've kind of run out of my time here. There's some more slides in here on controls. I'm not going to spend time on this right now because we don't have the time for it. But again, there's a copy of this on the website. But let me get to the point about operating costs. Albany, New York, a cold winter place. Let's say it snows 20 times a year there. So 20 times a year we have to turn it on and off. And Table 1 from ASHRAE already told us our annual hours of snowmelt operation. I think it was 156 hours for Albany when we saw that Table 1 from the ASHRAE handbook before. This is all the pieces of data that we need to know to be able to come up with kind of an annual estimate of energy requirement for doing this. But we can get all that. We can look at weather data. We know the cost of fuel. We know the efficiency of our heat source. We know how big the area is and that kind of stuff. So all this information is essentially known if you gather it and put it into the right equations. And I'm not going to show you the equations because I don't have time here, but on the version of this that's on our website, you will actually see the detailed math of doing this calculation. And for this particular ramp, it's going to use 30.3 million BTUs a year. Sounds like a lot. But the cost of that BTUs, if we're using a natural gas boiler running at about 95% efficiency, only works out to about $5.25 per million BTUs delivered to our hydronic system. 30.3 times 5.5, that's only $160 a year. That's it? That's not bad, huh? If we were going to sign a contract with Mr. Plow, remember there was a Homer Simpson, an episode a long time ago, he was going to start a job being Mr. Plow for the winter. If we were going to sign a contract with Mr. Plow to come 20 times a year and plow off this ramp every time it snows and keep going, keep it 100% snow-free during 90% of expected snowfalls, how much would he charge us to be there at least 160 hours out of the year, keeping that ramp snow-free? Probably a lot more than $160. And in fact, in people I've talked to, and it depends if you're in New York City or Madison, Wisconsin, or here in Chicago or wherever, but it could be many, many times more expensive to do that manually. So the average value that I heard when talking to a lot of people is it would be about $2,000 a year to hire somebody to come and keep that ramp clean versus $160 in natural gas to melt it away. That's a big deal, right? That's 90% cost savings, which translates into energy savings as well. And then the other advantage of the snow melt system, we're going to use an automatic detector and automatic controls, so it's always going to be on time. And at the end of it, when we plow it off, we don't have these big giant snowbanks left behind burning up parking spots as well. and creating melt hazards. Because as that snow is melting every day in the sun, and then it freezes up every night when the sun goes down, we're creating more ice hazards out in the parking lot. So I hope everybody will agree the snow melt system is going to be better for everybody involved. And is it an environmental big problem? Probably not so much, because we're using 90% less cost. That's almost like not exactly 90% less energy, but it's definitely less energy than using pickup trucks and snow plows to get rid of that snow. So I don't feel so bad. I really care about the environment. I'm quite a green guy myself. I don't feel bad about doing snow melt systems, because I really, truly believe this is a better overall environmental picture. Nobody's using salt. That concrete ramp is going to last forever because we're not pouring salt on it and stuff. The rebar's not going to rust. It's really better for everybody to have a hydronic snow melt system. So with that brings us to the end. Again, I apologize for running over time, but thank you for sticking with it. And I would be happy to take any questions. So the question was about, can we predict the cost of construction of building it, both the inside side and the outside side, things like that. Believe it or not, years ago when this system was a real system, I did get involved and I asked the contractors the pricing of how much did it cost you to put the tubing down, put the insulation down, build a mechanical room with the boiler and the pumps and the glycol and everything else. And this was like more than 10 years ago. But I'm thinking it was about $3, I think, per square foot for putting the tubing down in the insulation. And I'm thinking it was less than $20,000 to build this system. Now that was 10 some years ago, before COVID, COVID and everything else. But not that bad, not that bad. So from the audience, Patrick said a system like that would be maybe $25 a square foot, so $25,000 for this 1,000 square foot system, but that's Canadian dollars, so that works out to about $20,000 US. So yeah, in that ballpark. Keep in mind, you're pouring the concrete anyway, so the concrete is not part of the cost of building this system. The insulation is extra, and the tubing. The tubing is almost the least expensive part of this system, the tubing itself. The biggest part of the fixed costs in the mechanical room, like the heat source and the gas piping and all that kind of stuff. So, but good question. Thank you for asking about that. Any other questions? Patrick? So the question was the importance of sealing between the sheets of insulation. A lot of the insulation kind of comes with a bit of a tongue and groove to it, which mostly helps with that. But I don't think it's that important. Like, I wouldn't put duct tape on it or anything, because if any moisture is going to make its way through the concrete, it could just go through that gap into the earth anyway. And that's okay. That just kind of helps with drainage and getting rid of it. So I wouldn't be too concerned with that. Yes, sir. So great question. Does it increase the lifespan of the outdoor surface material, asphalt or concrete? Sure. I don't know. I haven't heard an actual report on that. If somebody was running an always-on system, let's say you have got a hospital, and the heat loss for the hospital is, 8 million BTUs per hour, and you've got 1,000 square feet of snow melt out front, you're probably not going to turn that system on and off. You're probably going to run that snow melt system from December till the end of March. And that way, no matter what happens weather-wise, that snow melt system is working at the hospital entrance, the emergency entrance or something like that. In a case like that, if you're keeping it at a constant temperature all winter long, that's really good for the asphalt, as opposed to having the asphalt temperature going up and down all day long. So in a case like that, I could see making the case that this is going to extend the life of the outdoor surface, but it's also extending the life of the outdoor surface because you're not driving the heavy equipment over it, the snow plows and the salting and that stuff too. Yeah, thank you, Dale, for providing a lot of these pictures to us. And a lot of what I've learned about snow melt comes from the contractors that were doing it even before I got involved. So there's a lot of great case studies out there and case history and things like that. This isn't just marketing stuff. It really works. These systems are proven. Yes, sir. So the question was about comparing an on-off system to an idle melt system, which is still keeping it warm in between snowfalls. So I actually kind of skipped over this slide, but I'll go back to it now. That's kind of one of the three general control strategies. The first one I talked about was basically on-off. You turn it on when you need to and turn it off in between snowfalls. But idle melt is exactly what you're talking about, where in between the snowfalls, you don't let it go to outdoor ambient cold temperature. You might keep it at 20 degrees or 25 degrees Fahrenheit. Maybe you keep it at minus 5 degrees Celsius, so that when the snow does come, you're not going from a cold start. You can warm it up much faster. Those systems, that type of control strategy is really important for high liability areas, like a commercial building entrance or office building or, the church or something like that. Residentially, I wouldn't do it because the annual energy cost of idling the system could be 4 times the cost of what you'd actually use for just melting. Depends on the city and how often it snows. But whenever I've heard a customer complaint where the customer come back and said, wow, the snow melt system costs a lot more to operate than I thought it would, it's because they activated the idle setting and they're keeping it warm all the time. And if they turn that off, then in a lot of cases, they'll reduce their annual energy usage by about 60, 75%. Dale had his hand up first. And the conversation is about idling versus on-off kind of systems. And it really depends to me on how often does it snow where you are. If you're in a place that only snows once a month for 8 hours, then keeping it idling the other, 600 hours that month might be considered a waste of energy because because how much energy does it take to keep the concrete at 25 degrees or 30 degrees Fahrenheit with the cold and the wind and the night sky and everything else? It can take a lot. But if you're in a place, maybe in Montreal, it snows every 3 days, in which case it does make a lot of sense to just idle and never really turn it off because you get really frequent snowfall. So to me, it's very situationally dependent on where you are and what your weather is. But you're right, control-wise, nowadays we do have these smart controls. I mean, any of us can look at our phone and find out that it's going to start snowing maybe between 5:30 and 7 p.m. tonight, and that's pretty accurate. Forecasting has gotten really good. If we feed that information to our snowmelt control, so it turns on the system 2 hours before the snowfall actually comes, then you don't need to idle it. You just activate it 2 hours before you need it, and it's nice and warm when you're ready to go. So those kinds of systems exist now, and that capability is out there for sure. Thank you so much. I appreciate it, and I'll stick around if you have any other questions.